Okay, so my screen is visible to you, right?
Yes.
Great, then I'll switch to this conversation mode and start today's topic is actually, I would say, a little bit different, but I just finished whatever I started and talked about in the last two classes. So thanks to our ability of encoding things into strings, we can now have computations defined this way. So I just recall. So given some subset L over sigma star, and okay, so L is a subset of sigma star, and some X in sigma, decide whether X is in L or not. Okay, so now this X is a string. Sorry, X is in sigma star. This is a subset, this is a member. Okay, so X is a string, it has a finite representation, so we do not worry too much about X. So what remains is to talk about is how I can represent a subset of sigma star which may be infinite. Okay, so exhaustive enumeration of an infinite set is not possible. So here are certain possibilities. So English language description. We may have mathematical descriptions. Okay. As I have done for the set of primes, the set of primes is basically an English language description, whereas the mathematical description that I have told yesterday is composed of arithmetic and logical constructs. And then we can also have recursive description. And this recursive description is in this context called a grammar. Finally, we will also see that we can design machines equivalent to these grammars. So by machines called automata. Okay, so we will start building simple machines today itself. But before that, I want to highlight that this description of a language has to be finite. Okay. I cannot simply feed an infinite description to a machine. Okay. So I am talking about sigma as the alphabet of input strings, but this description also has an alphabet. And let us give it a different name like gamma. This is the description alphabet, which may be different from sigma itself. Okay. And like objects, okay, graphs, numbers, we can also encode this description in the form of a string. Okay. And it has to be finite. Okay. So I must say that such a description, finite description of a language, is a string over the description alphabet gamma. Okay. Agree or not?
Yes, sir.
Okay. Okay. So now I will talk about, so this is a string over gamma that is a member of gamma star. Okay. All alphabets are finite by definition. Now let us see a frustrating consequence of this. Okay. Okay, what is sigma star? It is a countable union of finite sets. Each sigma power n is finite, right? And it's a countable union. So what is the size of this, countable or uncountable?
Countable.
Countable, great. So this is countable. Good. Likewise, if I look at this other alphabet, gamma star is also countable. Okay. Now, if I look at languages, languages are subsets of gamma star. So how many languages? Is it countable or uncountable?
Uncountable.
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 Because it is basically the power set of sigma star, which is countable, countably infinite. Okay. So languages are basically, this is the set of all languages, 2 power sigma star, and this is uncountable. So on the one hand, you see that there are uncountably many languages, or equivalently, there are uncountably many computational problems to solve. On the other hand, the requirement of finite representation of languages forces me to deal with only countably many descriptions. Yes or no? In other words, if I am given only a finite description, the possibility of finite description, then I can represent only countably many languages. Agree or not?
Sir,
Yeah, tell.
can a description describe more than one language?
What is the question? Can a description?
Can describe more than one language.
How can a description, I mean, for example, if you look at the English language description, the set of all primes, how can it describe 2 different sets?
Okay.
Right. Okay. So that means 2 things. First, having some sort of description, finite description of a language immediately does not say that I can build a machine for that. But one thing is obvious, since the set of finite descriptions is countable, I cannot build more than countable number of machines. Agree or not?
So can you repeat the statement?
Now, of course, if I have to go for finite representation, then I am talking only about countably many languages. Okay. It's not guaranteed that all these languages have corresponding machines. Okay. But one thing is clear that by using finite descriptions, I can address only countably infinite number of machines.
So what is exactly a machine here in this context?
I will come a little later. Only thing is that, okay, maybe this is the question. Let me draw a picture. Where is it? Yes, here. Okay, so this is our abstract computer. Okay, I am feeding to it L, I am feeding to it X, and it will output yes or no. Okay, and I will build a machine suitable to L and X, right? Since I can, and both X and L must have finite representation, I cannot simply supply the machine with an infinite sequence so that the machine will keep on just reading it forever without doing any computation perhaps. Okay. So this is my schematic, right? But our inability to deal with infinite representation essentially means the number of inputs that I can provide to a machine is only countably infinite. Okay. So if I look at all these LX combinations having finite representation, set of all these combinations is countable. Yes or no? This part you understand?
Yes, sir.
Okay. Therefore, it is out of the question that I can, okay, for every L and X, I may have one machine. Okay.
Sir,
Yeah.
I didn't get how the set of all combination of L and X is countable. Like we have infinitely many languages.
No. I am talking about languages having finite representation.
Okay, sir. And
Okay. X is a
okay.
string, it is anyway finite. So L is something having finite representation. X is anyway a string, by definition it is finite. Okay. So this kind of machines can be only countably infinite in number. Yes or no?
Yes, sir.
Okay. So if I state it in another language, computers can solve only agree or not?
Yes, sir.
Okay, this is one thing. Second thing is that there are uncountably many problems. Agree or not?
Yes, sir, because languages are.
Okay, so what is the consequence of these two statements? It is this, that computers cannot solve all problems.
Sir,
Yes,
sir, can you please explain the second point? There are uncountably many problems.
because I have identified problems with languages. For us, computational problem is nothing but a language membership problem. And we have seen that 2 power sigma star, that is the number of languages, which is the same as the number of problems, is uncountable. Agree?
Yes, sir.
Okay. So computers cannot solve
Sir?
all problems. Yeah.
Sir,
Sir,
then
those
can we
problems
say
that
that
computers cannot solve are they do not have a finite description, right?
No. First of all, I didn't say that. If I didn't say that if I even can describe a string over sigma, I mean, if I have a finite representation, I immediately did not prove that for whatever language I have a finite description that can be solved by computers. First of all, I didn't prove that. Okay. So there may be languages which can be described in English or mathematically or in some other ways, which cannot be solved by computers. Okay. In fact, we will see some such problems. For example, the halting problem. Okay. We will see many problems near the end of this course, which we can describe at least in English, more formally also, but these problems are not solvable. Okay. But one thing is that if some language, I would say, in a sense, does not have any finite representation, then this is definitely unsolvable. Okay, so there must be unsolvable problems. Irrespective of how powerful your computer is, there must be unsolvable problems. Near the end of this course, we will see many such unsolvable problems, which no machines can, I would say, address. But this is actually a negative thing about computers. But I would say that this should not come as a surprise to you. Can you represent all real numbers?
No.
It's exactly the same thing here. I cannot represent all real numbers. I have to live this life because of this countability, uncountability arguments. Okay, this is life. We cannot escape this so-called bad truths. Okay. So there must be unsolvable problems, and this is essentially the same as saying there must be Okay, this is, and this is, they are basically the same assertion. Okay, I would not say the same assertion, but equivalent assertions. There must be some numbers that we cannot represent in a finite amount of space. You add symbols, do whatever you want, but your representation, finite representation, means you are only addressing countably many numbers. And you are leaving out an uncountable numbers, uncountable, I would say, subset of the numbers, real numbers. Okay. Okay, so
Sir,
yeah, tell.
so the claim is that since number of languages is uncountable, and only
Yes.
countably many can be having a finite representation. So that is the claim here, right?
That is basically the thing. Yes,
Okay, okay.
exactly. This is precisely the thing. And again, as I mentioned, having a finite representation does not mean immediately that it is solvable. But anyway. Agree?
So can you give an example for this?
Yes. Please wait. We have not yet started the course. We will see many examples. Faulting problem and many issues, but for that we need to have some machines which we think as powerful as they can be.
So what do we mean by unrepresentable numbers? Like if we know a number, we know it. What is the meaning of this statement?
That's what I told. Pi. You cannot have a finite representation. It's 3.15, blah, blah, a huge sequence, an infinite sequence. So in order to represent it in that standard decimal notation, you cannot manage, right?
Okay.
But still pi is an important thing. So our inability to represent pi as an infinite expansion allows us or promotes us to introduce the symbol pi. So I will just use the symbol pi. This is now a finite representation with all its implications, meanings, connotations. Okay, so pi is now a finite representation of this irrational number, 3.141592653, blah, 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 whatever. Okay. But you cannot keep on introducing new symbols for every irrational number. Okay. You will eventually run out of symbols. Okay. So that's the point.
So it means even if we keep on introducing new symbols, we'll only be able to introduce countably many symbols.
Exactly.
But still uncountably many numbers won't be represented.
Exactly. That is precisely the thing. We can introduce even countably infinite number of symbols. Still we are addressing countably many numbers using those countably infinite symbols. Okay. Exactly.
So, pi, we use only the same digits as symbols representation.
What is that?
For the representation of pi, we use only we repeat the symbols to represent it.
Okay. We use symbols. 0, 1, 2, 3, maybe up to 9. You introduce symbols like pi, e, square root, cube root, fourth root. Keep on doing this. As long as this is the representation alphabet. And also, of course, you can also talk about plus, minus, things like that. So this is, let's say, the representation alphabet of numbers. Okay, let us call it sigma. With all connotations, you do this. introduce whatever symbols you like. I say that even if sigma is countably infinite, sigma star is nothing but sigma power n greater than equal to 0 is countable. Whatever symbols you introduce, keep some meanings and all that stuff, still you can address only countably many numbers. Yes or no?
Sir, are we representing each number with a symbol, like 0.1 with some symbol and so on?
0.1 is the string 0 followed by point followed by 1.
Yes, sir. So even pi also we represent by 3.14 and so on, repetition of
That's
J0
nothing
to
but
pi.
so on. That is not an exact representation. And so on should not be there. Okay, so if I say something like this 3.1415926535, I think this is up to 10 digits. Then if I put this dot 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 ellipsis sign, then I am not representing pi. This is not an exact representation of pi, right? What is this dot dot dot? Infinitely many symbols are left out.
Yes, sir.
Okay. Therefore, in order to represent pi, which happens to be a very important number in our mathematics, I just introduce the symbol pi. This now has a finite representation, just this letter pi with all its meanings. Okay, so you keep on introducing Greek symbols, Hebrew symbols, Devanagari symbols, Bengali symbols, Tamil symbols. Go ahead, do it. This set. And even you can think about square root, cube root, fourth root, fifth root, uncountably many symbols you can introduce this way. Sorry, countably many symbols you can introduce this way. Still, your representation alphabet remains countably infinite or countable. Yes or no?
Yes, sir.
Okay. And therefore, the number of numbers that you can represent using this countably infinite representation alphabet continues to remain countable. Okay.
Okay.
And exactly the same thing happens in the domain of computation. There will always be unsolvable problems, no matter how powerful a computing machine or automaton I can design. And of course, there is something called Church-Turing thesis that puts a restriction on how powerful machines can be. And this is just a hypothesis, but we will come to that little later. Okay, so this is an issue I wanted to tell you. And this is possibly one of the, say, basic reasons why we covered this countability and uncountability things in our discrete structure course. When we study Turing machines, we once again will come to this diagonalization and similar things. But let us wait. I just wanted to convey to you that there must be unsolvable problems, no matter how powerful machines we can build. Okay. Okay, so now before handing over to Professor Kole, I would like to mention that the way we have defined computation takes a finite description of a language and a string. It outputs this and this. Okay. This is how we defined it, right? But to start with, what I will do, I will build, or we will build, a set of machines which has in its head or CPU, whatever you call, a kind of description of L. And I will supply X externally to it. So the knowledge of L is now embedded in that machine. I am only supplying X, and this machine is giving output yes or no. So in other words, this machine can solve only one problem, the problem associated with L. Yes or no? Do you understand the difference between this and this?
Sir, only one problem or the problem for only one language?
Problem and languages are same, right? That's how we define problems. Every computational problem is associated with a language. It's a language membership problem.
Okay, sir.
Okay. So in this setting, this machine can solve only the membership problem for L. That means I have one machine for primality testing, one machine for, let's say, connected graphs, one machine for palindrome checking, and so on. But our computers are not like that, right? Okay. If you want to, for example, check primality, you write a C program for it, compile it, run it. If you use the same machine for, let's say, minimum spanning tree computation, you write another program, do it. So a single machine capable of solving all problems is definitely what is our ultimate goal. Okay, not machines like this that can solve individual problems. Yes or no?
Yes, sir.
Okay. So near the end of this course, we will build a machine called the Universal Turing Machine that can solve this kind of problem. But before doing that, we will keep on building machines specific to specific problems or languages. Okay, so this is called the Universal Turing Machine, a single machine that is capable of solving all computational problems.
Sir, such machine does not exist, right?
This machine exists.
Universal Turing machine.
It exists. So at the end, we will see how we can build this machine, but its language itself is a little bit complicated. Anyway, this is too much ahead of doing the real things.
Sir, existence, are you saying theoretically or practically?
Yeah, we will see how to build universal Turing machines. It's fairly straightforward.
Sir,
the
but
issue
you
is-
have said computers cannot solve all the problems.
No, universal Turing machine can solve all problems that computers can solve.
Oh, okay.
Okay. Yeah. But before reaching this stage, we have a long way to go. We will start language-specific machines. Eventually, we will design machines that can solve all computational problems that machines can solve. Okay. So I think I stop here. This is already a long introduction. And we are still not in the course proper, except for some definitions. Sigma, sigma star, sigma power n, concatenation. Okay. So I think I stop here. If you have any immediate questions, let me know.
Sir, you talked about a recursive definition of a language. Could you show an example, please?
We'll see, we'll see, we'll see. Please wait. Okay.
Okay.
Okay. Everything we will do, but in due course of time. This is just a very brief overview and a motivation why we are doing these things. Nothing more than that. Okay, so shall I stop here and hand it over to Professor Cole? Okay, she will now start building machines today itself. These are very restricted kind of machines, but good to start with. Okay, I will once again come back. Let her proceed for a few days, then I will once again come back. Okay, so I am stopping my presentation.
Professor Das, will you stop the recording and I'll start again, or will this continue?
I think we can continue, no problem.
Can you please confirm whether you can see my screen?
Yes,
Yes, ma'am. It is
yes,
visible.
ma'am.
Okay. Okay, so you have had an introduction to why we study, we want to study formal languages and automata theory. Mainly the motivation was, one of the motivations was that we want to understand, suppose I have a computation system like a computer, we want to understand what kind of problems are computable there. You have had a brief idea of the fact that all languages are not computable, but at the same time we also want to understand which ones are and which ones are not. Also, suppose you have a computer and let's say you have another computation system like let's say a calculator. You want to also understand, is a calculator as powerful as a computer, or you think of any other computation system. You should be able to compare what kind of problems are solvable in these computation systems. But for the time being, you also have to keep in mind that we are not at the stage where we can think of taking in a problem as an input. So we will start slowly. And the objective is to mathematically model these computation systems such that we get to understand the computational power of these systems. To start off, as Professor Das has said, we will be problem specific. A particular machine will be solving for a particular problem. And the first models that we are going to be looking at are finite automata. This is again a very abstract way of looking at computation systems. We sort of leave out, we only look at the most important parameters that define the computational power of these systems. We will leave out some of the non-parameters, which, the mathematical modeling will help in identifying which are the parameters which which capture the computational power of these systems. Okay, so let's get into some of the things that we should keep in mind when we are trying to build a machine model. So the first thing is, what in a machine model, if I look at a machine, then I am always going to be interested in how the machine is transitioning or how the machine is doing the computation. When suppose you are using a calculator, you are going through certain steps, and you want to capture this logical process of computation in your machine model, and this is what is going to be called a state of a system. A state of a system is going to capture the description of the system at a particular time step. So that means any information that captures any information that is sort of a snapshot of that system at that particular time step should be included in the state of a system. Not only that, I should also have information to determine what the system is going to do in the next time step. This is what will capture the progress of the computation in that particular system. So one is, what is the current status of the computation system of the machine, and second is, what is going to happen in the next step. So these two, all information that corresponds to these two topics is going to be captured in the state of a system. Next is another important thing. When I talk about what is happening in the current time step, and then I say I should also know what's going to happen in the next time step, that means I should be able to define what are the changes in these states. The current state gives us some information about what is happening now and what can happen next. And I should also have a way of capturing this change from one state to the other. This is called transitions, and they can happen in two ways. One is it happens spontaneously because of so currently we are in the framework where we are looking at machines which are solving a particular language. So it is possible that the description of the transition is inbuilt. Some things can happen spontaneously, or the transition can happen in response to an external input. For example, you have an alphabet alpha, you have an alphabet sigma, and you are getting an input string where every alphabet is coming from sigma, and depending on how the input string is coming in, how the machine reads these strings, these alphabets one by one, the machine goes to the next state. There is one mathematical assumption that we will be making, that is when we are at a particular time step, we are at a particular state. So these transitions can be thought of as instantaneous transitions, meaning that at a particular time step I am at state, let's say 1. In the next time step, I will immediately go to state 2. If the transition is from state 1 to state 2, we will be assuming this. It's not going to be as if from 1 I can go to some intermediate state and then finally I end up in state 2. And these are not, these are not far off mathematical assumptions, because if you think of clock cycles in digital computers, so clock cycles help in maintaining the fact that in a particular time step, the processor is making one calculation. Broadly speaking, in a particular time step, one step of calculation is done by the processor. And so clock cycles exist, and therefore this is not a very far off mathematical assumption that we are making when we are saying that in a particular time step, we are at one particular state, And in the next time step, we immediately go to the next state according to whatever the transitions guide us, however the transitions guide us. Finally, now we can talk of a machine as a state transition system, where this system is modeled in terms of the states, which says what the machine is doing currently and what it is supposed to do in the next step, and transitions which help us to go to the next state. And some of the examples are like a digital watch or an elevator, where an elevator, you can think of what are the states. Let's say stopping at ground level, then stopping at level 1, then stopping at level 2. You cannot stop in between. Then the configurations of a Rubik's cube, etc. Now we are going to make the first model that we are going to be looking at. We are going to make it as simple as possible. So what we require as well is that the system has finite states. There are only finite many snapshots that the system can have, and also they have finite transitions. So this will be called a finite state transition system, and we are going to be looking at the mathematical modeling of such systems. These will be called finite automata.
Excuse
So
me.
now, yes.
Ma'am, what is a finite state? Means it refers to finite number of states or anything else?
Finite number of states, yeah. Finite number of states and finite number of transitions.
Okay.
So we will look
Ma'am, if
at,
the number of states is finite, then number of transitions will also be finite, I guess.
yes, that's true. So basically we are currently we are just looking at the number of states. We are saying that that is finite, and the transitions can happen between these states. So that would mean that the transitions are also finitely many.
Okay, ma'am.
So let's look
Ma'am,
at the
all states are
mathematical.
unique,
Sorry?
or are all states unique?
Yes, you can think of all states to be unique. It is possible that a transition, suppose, so we said that transitions can happen automatically, instantaneously, because of maybe some description of the language or description of the problem, or it could happen because of an input alphabet. It is possible that you stay in the same state even after reading an input alphabet. This is possible. So the transition could be that the system stays in the same state even after reading an extra input alphabet. But the states you can think of as unique.
Okay, ma'am. Got it.
Okay. So now let's look at the mathematical representation of whatever we described in words in the previous slide. So you can think of a deterministic finite automata, of a deterministic finite automaton as a tuple. You think of it as a vector. So this is, you can call it M, just any generic name, let's say M, which is equal to this tuple, this 5 tuple. Now what are the components of this tuple? The first component is Q, which represents the finite number of states. It's a set, it's a finite set, or a set which has finitely many states. Next is the alphabet. Again, it's a finite alphabet, meaning finitely many symbols in the alphabet in this set. And this is sort of from where the input symbols are coming in. So if you think of the input string, you can think of it as a sequence of these, a sequence of these symbols from this alphabet sigma. Next comes delta. So in the current most basic mathematical representation, we will only be thinking of delta as a transition function, meaning that you give me any state and you give me any input alphabet, I should have a proper definition for this machine. So meaning that you give me any state Q and any input alphabet, I should know what the next state is going to be, what the transition is going to be. And this is a finite set of ordered pairs. So as somebody pointed out, currently this is a finite alphabet, this is a finite set, and this is a finite set. So the number of transitions, the number of possible transitions, even if I want a proper definition for every state and every alphabet, is still going to be finite. The fourth component is a particular state, which we are going to say is a start state. So now you can imagine that this is also another layer of simplification in the first mathematical modeling that we are looking at. When we are specifying that, okay, there's just going to be one start state. We could have said, no, there are many start states from where I should have a choice of starting from many of these states. Instead of that, we are just keeping it as simple as possible. And we are saying that there is exactly one start state from where the machine starts. So no matter what the input is, the start state is a particular state. We are calling it S. And then you also have some special states which are called final states. Since it is a subset of the entire set of states Q, that's also going to be a finite set. So now notice that if you just look at this 5 tuple, you have a finite set of states represented by Q, a finite set of symbols that is denoting the alphabet sigma, a finite set of ordered pairs denoted by delta. You have one special state, which is the start state, and you have a finite subset of special states called final states. So in total, this can be represented as a finite string. You just pick any favorite encoding. One of my favorite encodings, which is quite clean, is you just write, suppose you write 1 to the length of Q, then let's say you add an extra symbol hash, then you write 1 to the size of sigma, then you add hash, and then so let's say, so now if you have Q and sigma, you can think of Q to be states 1, 2 till size of Q. You can think of sigma as, let's say, I'll just write it as 1, 2, and then the Roman version of size of sigma. And now this delta you can write as, so you first have to denote which Q it is. So let's say I want to denote, so let's say delta currently is of the form, so if it is at state 1 and it reads alphabet 1, I want to say that this goes to, let's say, state 2. So one way of, and then there are other such pairings. One way of doing this is I write 1 and then I write, let's say I put a 0, and then I put another 1, then I put a 0, and then I put, let's say, 1, 1, and then I put a hash. So this will sort of denote this particular transition. So there are different ways in which you can pick an encoding and denote this entire description of a particular machine the way we want it. In the simplest form, if you give me Q, sigma, delta, S, and F, I will be able to give you a finite string that represents this. So so this, is there a question?
One to the power mod Q.
Sorry?
1 to the power mod Q. I mean, what is that representation?
So this will just be Q many ones. Now mod Q many ones.
Okay, they're written side by side, 1, 1, 1.
Just just.
And ma'am, can the
ones.
start state be an element of Q?
Yeah, start state is an element of Q. you can also denote that in a particular, you can, whichever is the start state, suppose 1 is the start state which you want in your particular description of the machine, then you just write that particular so let's say Q is the start state. So when you come to the portion which reads of the start state, you just write a unary string of length mod Q.
Ma'am,
And
why
you
the
can,
final state is subset of Q? Why can't it be the whole set Q?
it could be the whole set Q. I'm just saying that it may be a subset of Q. That's just, I'm just leaving a leeway where you can make it a subset of Q. It could be one state, it could be a subset, it could be the entire Q. I'm just saying that we are specifying certain states to be final states.
Are we saying that there can be some transitions to which only single final state can be achieved? If F has a single element, single state,
right.
Then any transition make to the
No.
start state.
No, I'm not saying anything like that. A transition could be between any two states. I am just specifying a particular start state. So let's say from a start state you transition to, let's say the start state was 1. So from a start state, suppose you transition to 2, and then maybe the transitions are such you just remain in 2. No matter what alphabet you get, the transition function asks you to stay in 2. But the final state, maybe the final state subset only contained 3. So it is possible that I don't reach 3 at all through the transition function. All this is possible. This is a very abstract definition. I'm just saying that you have a finite set of states, you have a finite set of symbols to denote your input alphabets. You have, because your set of states and your the number of alphabet symbols is finite, you also therefore have a finite set of transitions. And just one simplification is that you require this kind of machines, these kind of machines which fit this model, this mathematical modeling, you require them to start at a particular state. And there may be some special states which I'm going to call final states. I will tell you why this is required. So basically you want, as you have seen, you want a particular machine to be solving a certain problem, right? So you want a machine to solve, let's say, a problem L. Let's say this machine M. I want this machine to solve this problem L, and as in the previous diagram, let's say this machine has some encoding of L, which basically means this particular tuple is in some form hardwired into this machine. And now you get an input X, and you have to answer some yes or no. So how you answer this yes or no will be dependent on whether you land up in a final state or not. We still haven't gotten there. There are certain states which will help you in determining whether the answer is yes or no. Okay?
Okay, ma'am.
Oh. Yes?
What exactly are we trying to encode in this last one as this one?
This one? This is just, I just gave you, I made this statement, right? That if you look at this particular structure, you can encode it in any you can think of it as a finite string. You just think, just in English language, you can say Q is, let's say Q1, Q2, Q size of Q. And then sigma is, let's say A1, A2, A size of sigma. Then delta will be a set of pairs of Qs and all possible Qs and As and the resulting function value. Then you have S, and then you have the final state. This will also be, let's say Q1, Q2, and so on. So this is one way of writing it down. Since all of these things are finite, you can write it down as a finite length string. You can also be more specific. You can in fact write it down as a binary string as well. If you want to do it, one way of doing it is the way I was talking about. It's not fully binary. I use these hash symbols, but you can replace it by a certain number of zeros. You can try and see how you can also represent this, whatever I have written in English. You can try and see whether you can represent this in terms of zeros and ones. So it's not just any finite string. You can also represent it as a finite length string in zeros and ones. You can do whatever you want. If this is finite, there is, no matter however you, in all reasonable ways that you want it to be represented in a finite manner, you should be able to do it. Okay, so this machine, this abstract machine, can be represented by a finite string. Even if you said, okay, I only want binary strings, my claim is this machine can be represented by a finite length binary string.
Okay, ma'am.
Okay. But now, yes.
The input to the machine is a symbol, and the set of such symbols is sigma, right?
The input to the machine is a sequence of symbols. The set of the symbols is sigma, but it is a sequence of symbols.
Then state transition function should be q into sigma star.
No, so so input is a sequence of symbols. Why do I say sequence? Because at every time step you can think of the machine reading one particular input symbol. In the next time step, it's going to read the next symbol.
Means to perform one operation, it will require only one symbol. Then it can take the next symbol.
So you can think of x as x1 to, let's say, xn. N is some variable. And at every time step, in the first time step, it reads x1 and then does some transition depending on where it is state-wise. Then it goes to the next symbol. In the next time step, reads the next symbol, does the next transition, and so on.
Okay.
So in the transition function, you only need the current state and the current symbol that the machine is reading.
Okay.
So one question, one follow-up question is, suppose you had sigma star, would it still be a finite description? I don't know who asked the question.
And if the strings that we are, we can only input finitely long strings, so it would work. Like,
no.
I don't think it will work because sigma star is countably infinite.
Sigma star is countably infinite, correct? Yes. So if you look at a particular string, sure, it is of finite length, but sigma star is countably infinite. You can take this x belongs to sigma star. So any so if you look at q cross sigma star, instead of sigma, if you consider q cross sigma star, what would this set be? So you have a finite set, product, a countably infinite set.
Countably
infinite.
Correct. So we don't have a finite description of this transition function delta if we consider that entire x as part of input. So the modeling itself, if we want a finite model, we should be reading it one symbol at a time. So now let's look at a concrete example where we specify what is q, what is sigma, and so on. So let's look at M, and we are specifying q. We're specifying q to be 3 states. They are named 0, 1, 2. Then we are specifying the alphabet to have 2 symbols, A and B. And I am also specifying the transition function, notice that this is a function because for every state and every alphabet, you have a description of there is an output of the function. So 0, when you're at state 0 and you're reading A as input, you are transitioning to state 1. Similarly, 0B results in transition to state 0. 1A results in 2, 1B results in 1, 2A and 2B. So if you're at state 2, no matter whether you read A or B, you should remain in 2. This is what this transition function says. I'm also specifying the start state to be 0, and the subset of final states only has the single state 2. So this is a concrete example that fits the mathematical model we were talking about before. I have specified each of the components of this 5 tuple. But what does this actually mean? So I have designed a machine where I have specified each of the 5 tuples, each of the components of the 5 tuple. But what does this actually mean? What is it computing? So in order to understand that, let's try to visualize this further. So one way of doing it is a transition table, where basically we have to visualize what is happening in the transition, right? In the transition function. And this is a 2-variable transition function. You can think of it as a 2-variable transition function. So you can always visualize it as a table like this, where the rows correspond to the states, the columns correspond to the input symbols, and then depending on and each of the elements corresponds to the state and the input symbol that we are currently at. You also have some special some extra information. For example, 0 is a start state, so you can mark it with an arrow. I've used colors. You don't need to use colors, but you can mark this particular, just to denote that this is a start state. You can mark it with an arrow. All the states which are final states, you can indicate that by just writing an F after that state. So this, you can think of this table with some extra symbols is denoting the entire machine. You are visualizing the entire machine description of this particular n. This particular n that we have specified, you can visualize in terms of this table. But we are still not very clear as to what are the strings that, let's say, if we wanted to ask the question, okay, what are the strings that start at 0 and are ending at 2? If we were interested in finding out these particular set of strings, this table is not really, visually it's not giving much details. We may have to work things out, and it has all the information, but visually we are still not getting enough details. So another way of visualizing it is a transition diagram, where you're basically drawing a directed graph here. So the nodes of this graph are named after the states, so 0, 1, 2. And you are sort of indicating the fact that 0 is the start state, the unique start state, by putting in this arrow at this node. So any input alphabet, so any input string, you should start from this particular state. Now, the final state, the set of final states, we can specially indicate by putting in a double circle around this particular node. So if you had a node like this, you're just indicating it by putting a circle around it. If you had more than, let's say, 1 and 2 both were final states, you can mark that with this extra circle around the node. These are just ways of identifying which are the final states, which is the start state, and so on. The most important part is, how do I visualize the transition function? And this is very natural, right? If you have 2 nodes and you are sort of trying to visualize what is happening from one node to another, you use edges. And in this case, you are using directed edges and label directed edges. The labels are indicating the second input in the transition function, the second variable in the transition function, which is the input alphabet. So if I wanted to visualize state 0 on reading input alphabet A goes to state 1 in the next step, what I do is from the node corresponding to 0, I put a directed edge to the node corresponding to 1 and I put A on top of that. This denotes the transition from 0 to 1 when the machine is reading the alphabet A, the symbol A. So is the visualization clear? What we are trying to do with the transition diagram? It's basically a DAG, a labeled DAG, where we are trying to capture this entire machine. If you give me a specific deterministic finite automaton, I will be able to visualize it using this labeled DAG and some extra symbols to denote the start state and the final state.
And is it necessary to be a DAG?
Yeah, right. Because you need to know where the transition is happening. These are ordered pairs, so you need to know how the transition is happening.
And can't it be
acyclic? Why is acyclicity required?
I didn't catch your question. Can't it be?
Why can't it be a cyclic directed graph?
Can't it be a cyclic directed graph? Sorry, I didn't get your question.
I mean,
Once
there
more?
can be cycles.
Of course, there can. So, for example, this is a cycle, right? Oh, okay. Sorry. I'm saying DAG. Sorry. I meant a directed graph. A label directed graph. Sorry, not a DAG. A label directed graph. Okay, so this can be visualized as a label directed graph. Of course, there can be cycles. Okay.
Okay, ma'am.
Okay, so now, of course, there was this original question that I asked that, I am getting a string as an input. Here, so far, I have captured what happens in one step. I captured it quite well by just labeling each of the edges. So if I want to see what happens in two steps, so for example, if I had, suppose my string was, so first, suppose my string was A. Then can you tell me where I will end up if I followed the transitions? I know that I'm going to start at 0. Where will I end up? After one.
State 1.
I will end up in state 1. If I had, let's say, A, B, then can you tell me where will I end up?
Same.
Same. Why? Because you're just following the directed path from A. When you read A, you know you're at state 0, you go to state 1. Now you're at state 1. You have to follow the directed path labeled AB. So if you are visualizing one transition step, you are following one directed edge, which is labeled by that particular symbol. If you want to see what happens which state I am at when I have made, let's say, I transition steps after reading an I length string, then you basically have to follow an I length labeled path. That label will be exactly this I length string, correct?
Ma'am, can you repeat, please?
So suppose I am looking at one step transition. What I'm doing is I'm looking at my current state. I look at the symbol which is going to make this transition happen, and I'm going to follow the edge named by that particular symbol. So for example, if the symbol was A and I'm at state 0, then I'm just going to follow this particular edge labeled by A, and I'm going to see where I end up. So I end up in 1. Suppose I have an I length string. So here you have, let's say, a 2 length string. What do you have to do to see where you end up after reading a 2 length string? 2 length string means I am going through 2 transitions, right? 2 steps of transitions. So what happens is first I read A, which means from 0 to 1, I follow this edge labeled A. Now I read B. That means from 1, I look at the edge which is labeled B. This edge comes back to 1. So I am at 1. But what I did in the process is I followed a path which is labeled AB from 0 and saw where I ended up. So if I am doing a one-step transition, then I'm following an edge labeled, a directed edge labeled by that symbol. If I'm doing, let's say, an I step transition, meaning that I'm reading an I length string, and every time I read an alphabet of that string, I am making a transition, right? From the particular state I am at. I could end up in the same state, but I'm still making a transition. So I am actually, in the transition diagram, I'm actually following an I length path, which is labeled by this I length string. Fine?
Yes, ma'am.
Ma'am, once we go to a final state, then do we have to stop there?
Once you go to a final state?
Yes, ma'am.
No, you don't have to stop there. It depends on what you're getting as input. So for example, let's try that. So if I gave you okay, so in this example, I can't do anything. Let me try another example.
Then ma'am, what is the significance of this F?
We'll come to that. We'll come to that. No, okay. I can't do much. So let me try another. Or no. Let me do it later. Let's finish this example and then I'll come back to the question that I don't know who asked this question, but the question was that if I'm at a final state, can I go to? Do I have to stop, or can I still read input alphabets and go to other states? That's possible. It depends on what your transition function does not stop you from going to another state if you're currently at a final state. Nowhere in the transition function definition do you have any restrictions like that. So it's possible.
Ma'am, then what is the significance of final state?
Yeah, we'll come to that.
Okay.
Okay. So yes.
Do we return yes? I mean, the output is yes only if the final state is, I mean, if the string reached a final state.
Exactly. Yeah. So, okay. So you are a little bit ahead of the slides. So basically the idea is that if at the end of reading the string, the input string, you are still at you end up at a final state, then the machine is sort of answering yes. If you don't end up in a final state, then the machine is answering no. Okay, so we'll look at this a little more. So far what we have seen is that if you give me an input string, which means a sequence of symbols from sigma, then we are basically in the transition diagram, we are following a path to see in what state this machine ends up in when the input string is completely read. Okay. So now, as somebody pointed out, we will say a string is we will say that a string is accepted, or that the machine is saying yes if the end state is F and it is rejected otherwise, or the answer that the machine is giving is no. So this is different from the previous question. It's not necessary that you enter a final state and then you have to stay in the final state. That is only determined by the transition function. The transition function has no restrictions on whether you have to stay in a final state or you can move out. It depends on the transition, the way you are defining the transition function. It is possible that after you have read a prefix of the input string, you may have entered a final state, and then as you read on, you may exit the final state also. You may go to a non-final state as well. What matters is, if after reading the entire string, if you end up in the final state, in a final state, then you say that the machine has said yes for the string, or that the string has been accepted by the machine. If it is rejected, so if it does not end up in a final state, if it ends up in a non-final state, then you say the machine has rejected the string, or it has said no for the string. Okay. So let's look at the example which we saw previously. So this is the diagram that we saw. You have three states, 0, 1, 2, and these are the labels that indicate the transitions from one state to another. This indicates the transition function. 0 is the start state and 2 is the final state. Now, can somebody tell me what are the strings that are getting accepted?
Strings having at least 2 A's.
Why are you saying that?
Because otherwise there is no path from
It goes to 2.
start to end.
Right, but why are you saying strings that have at least 2 A's? I mean, what is the characterization for that?
Because once we reach to
Whenever
it
we
and
get 1 A, it gets to 1, and then the second A takes it to 2, and it stays there.
Yeah, so you need to give two. So you said a specific statement, right? You said that this machine M. I am just nitpicking a little bit. This machine M accepts strings with at least 2 A's. So one direction of the argument is that M is accepting. So if M gets a string with at least 2 A's, then yes, it ends up in a final state, and there's no way of exiting the final state. That's why if you have any string that has at least 2 A's, I am going to finally finish at the final state, and therefore I'm going to be accepting it. What about the other direction? Is it possible to have any other kinds of strings which are accepted by this machine?
No.
No,
So
For
what
getting
is your
accepted,
argument
it
for that?
needs.
Huh?
For getting accepted, it needs to go from 0 to 1 and from 1 to 2, and both of which are done by getting A's as
So
input.
basically, if you look at any path from the start state to the final state, any string that is accepted, there has to be a path from the start state to the final state. Any such path will contain at least 2 A's. This is why the set of strings that you told me is actually a characterization of the language that is being accepted by M, or the problem that is being solved by M. You have already seen that the two things are the same. A problem can be thought of as a set of strings or a language. Okay, so I just wanted to point this out to you. So there are two directions to the argument. One is you argue if you want to characterize the set of strings that are being accepted by a particular machine, or the set of strings in this language that is being defined by this machine, you have to show that this machine accepts this set of strings, and in the other direction you have to show that these are the only strings that the machine accepts. So just keep this in mind when you solve further problems. Okay, so as you guys pointed out, if I had let's say BA, BBB, notice that I start from the 0 state. I take B, then I go to A, then I stay in B, I make 3 loops in B, I end up in 1, which is not a final state. If I take B, A, B, I do B, and then I go A, and then I stay over here, I end up here. So these are some examples that you can try. And then, as we argued in the previous slide, if you have to accept, if you give me a string with at least 2 A's, it is going to end up in a final state. And if you look at any string that is accepted by the machine M, it means that it must correspond to a labeled path starting at 0 at the start state and ending at 2, the final state. And notice that any such path must have at least 2 A's. So this is a proper characterization of the language. Okay, so now we need to formalize what we are saying in terms of a string corresponding to a labeled path in the transition diagram. We have noticed that we have formalized the fact that a particular transition corresponds to a directed edge in my transition diagram. So a one-step transition, in the transition diagram, a one-step diagram a one-step transition is corresponding to a particular edge. What we need to formalize is that a string, a one-step transition means I have read one alphabet, one input alphabet. If I'm reading a sequence of alphabets, if you look at the input string that is coming in, I need to formalize the fact that it corresponds to a particular labeled path in the transition diagram. How do we do this? So as I said, processing one input alphabet is formalized by the transition function. Now I need to extend this transition function to a multi-step transition function to capture these paths that I'm talking about, the multi-step transitions that are happening. If I read a particular string as input, this has to be captured, and we capture it by the following mapping. I'm calling it delta hat. It's an extension of delta, which takes as input Q, a state Q, and a sigma star, and it outputs the final state. This is how you can visualize it. You have you're starting at a particular state Q. You are getting a string as input. This is sigma star, which means you are using multiple steps of the transition function, and finally you're ending up at a particular state, let's say P. This has to be captured by delta hat. So these multiple steps have to be captured by delta hat, and one way of doing it is defining it as delta hat Q when it's reading the empty string, meaning that I have not gotten any input symbol, then it stays in Q itself. And here is the inductive definition. If delta hat is reading Q and the string XA, where the last alphabet read is symbol A, then this can be defined in terms of delta and delta hat in the following way. It is delta of delta hat QX, comma A, meaning that look at the inductively you have a definition for Q and the smaller string X in terms of the multi-step transition function delta hat, and after that wherever you reach, this delta hat QX will be a state. Let's call this P, and from P it is so delta hat QXA will just be delta of P comma A. So one thing that I have not specified is I'm calling this a function. I have not proved that delta hat is a function. Please try to prove it yourself using the inductive definition. Yes?
A is a single symbol, right? Here.
Single symbol, yes. So the string that I'm talking about, X is a string, A is one symbol. The last symbol of this string XA is A.
Okay.
So basically this is capturing the fact that I use delta hat Q on a smaller string X to reach. So delta hat Q on a smaller string X is basically some state P, and then the final state will be in accordance to the single step transition function delta. Yeah, so as I said, this sort of captures the fact that each step is determined by delta, and the induction step is saying that Q on reading XA, the string XA, reaching Q dash, according to the definition of delta hat, is same as Q on reading the substring X reaching some state P, and then on reading this singleton alphabet A, the single symbol A reaches the final state Q dash. I won't say final state, reaches Q dash, which is the output of delta hat. Okay, so this is what the induction step is trying to capture in this definition. Delta hat QXA is delta of delta hat QX, comma A. Now notice that if I give you a length 1 string, then delta hat and delta will agree. How do I prove that? So delta hat QA can also, this A can also be, A is a singleton symbol because we are only considering length 1 strings. A is a singleton symbol. I can also write A as a string in the following form, epsilon concatenated with A. Now if I look at the inductive definition step, then this can be rewritten as delta of delta hat Q epsilon, which is then reading A, the single symbol A. But if you consider delta hat Q epsilon and you consider this definition, the base case definition of delta hat, then this is just going to be Q itself, right? If I don't have any input symbol, then I'm going to stay in the same state. So delta hat Q epsilon is going to be Q, which, so this entire expression reads as delta QA. So delta hat QA can be shown to be equal to delta QA, meaning the delta hat and delta agree on length 1 strings. And finally, once we have this definition of delta hat, which is a multi-step extension of delta, then we can specify that X is accepted by the machine if delta hat starting from start state S and reading input string X, does it end up in a final state or not? If it ends up in a final state, then X is accepted, otherwise it is not. Okay, any questions so far?
Ma'am, delta hat does not have a finite representation, right? Because
Correct. Okay, very good. So delta hat does not have a finite representation. Why? Because one of the delta hat is defined on Q and sigma star. Sigma star is infinitely, countably infinite. So if we had a finite representation of delta hat, then life would have been much easier for us. We would have been able to use delta hat. We didn't have to use delta at all, because ultimately we are getting input strings. We are not getting alphabets. We are getting input strings for this machine that I'm talking about, M, which has description L. I am getting a string X, and I would like to know whether the machine is accepting or not. But since the input strings come from an countably infinite set, we cannot directly, in the simplest model that we have, we cannot directly represent what the machine is going to do on this entire string X. That's why we are thinking of X as a sequence, and one by one at every time step we read a new input alphabet, and then we process what happens to the machine in the next. When I read this particular input symbol, I process what the machine will do in the next step. Okay, so can you also tell me? Yeah.
Ma'am, but we can represent delta hat in a finite representation using the above recursion, right? We can first represent the delta in its finite representation and then use the definition of delta to represent delta hat in its finite representation.
Yeah, but here it's very dependent on what I am talking, what I have in Q and XA, right? So XA is coming from a countably infinite set.
Yes, ma'am, but the description can be finite.
You mean? So yeah, sure. I have written it. I could say for all Q, for all. Yeah, how is it going to be finite? Yeah, I mean in English I can say for all X in sigma star. This description as the inductive description.
But ma'am, the for all X in sigma star is not finite.
Yeah, this you cannot, mathematically you can't represent it, right? So same as, let's go to the previous example. See, this thing, look at the strings, all accepted. I have written this in English. This is a representation of the language. But what are the number of strings? What is the actual size of this set? It could be infinite, countably infinite. The number of strings that have at least 2 A's can be countably infinite. But what we are doing is we are finding a finite representation. Either you can think of it in terms of this transition diagram, or you can think of it in terms of the tuple that any of these 3 formats, the transition diagram or the transition table, or just writing down the description of each of these tuples. But notice that here, I have written down everything. There is no hidden. So this is a mathematical expression. If you can, this is a mathematical expression. You have some variables, and then you have one particular function, and you have some more special variables. But if you try to write down delta hat, you cannot describe it completely in a mathematical sense. You can write it down in English, saying that for all x in sigma star and so on. But you cannot write down the definition of the function the way you're writing it down here. You don't have the entire mathematical definition of the function. You won't be able to tell me if I gave you a particular it's not explicitly said. The entire function, if I gave you a particular q and a particular x, then implicitly, because of delta, you will be able to compute. But explicitly, you don't have the representation of the function in a finite way.
Okay, ma'am. So basically, a finite enumeration is not possible.
Yes. So okay, here. So basically, these are when I'm talking about the description of these functions. Yeah. Okay. Sure. You use the word enumeration. You are enumerating all the pairs, ordered pairs that are there in delta. You're enumerating everything that all the states in Q. You're enumerating all the symbols in sigma and so on. But if you have delta dash, then explicit enumeration is not possible.
Okay, ma'am. Understood. Thank you.
Okay, so where were we? 1 minute. Right. So another thing that came out of this is, again, if I go back to the previous example, so this is something this set of strings that must have at least 2 A's. We have an English language description. We have a mathematical. We have a graphic diagram, and we also have a mathematical description for this particular set of strings. But the actual set of strings is actually infinitely many. Right. So this is a very interesting thing. We can define. We can represent it in such a way that even if we don't, it will not be possible to enumerate the entire set of strings that must have at least 2 A's, at least not in a finite way. This can be countably infinite. But if I can draw this particular diagram, and in only this much space, I am just using this much space on my screen to enumerate. I'm using this much space to represent each of the this entire set of strings. So if you give me any string, then I will be able to find out what is the final answer for that particular string. Okay, yeah. So using the function delta hat, we can finally say that x is accepted by the language if delta hat sx ends up in F. Otherwise, it is not accepted by the language or the machine. We will be using the language and the machine interchangeably because they are one and the same. The problem and the language are one and the same. And currently we are dealing with machines which are problem specific. So we will be using these interchangeably. So again, the language accepted by this particular machine is the set of strings X such that delta hat Sx belongs to the set of final states F, and such a set is called a regular set. This is just a name for the for such sets. A is called a regular set if A is a set of strings accepted by a DFA M. So let's look at another example. Let's look at the set of strings X where each symbol is coming from the set AB. So X is from AB star, and additional property is that X contains 2 consecutive A's. So is this set a regular set?
No, ma'am. It is a
Why?
subset. Because we need not have 2 consecutive, means we can have some B's in between 2 A's.
No, but can you design, so of course the previous DFA will not work. Can you design a different DFA?
Right. Yes, ma'am. Like we can define 2 of B is equal to something such that it always
Okay,
gives.
can you just tell me the states and so on?
I will have to think about that, but it.
Okay. Take 2 minutes. All of you take 2 minutes.
Yes, ma'am, I can do it.
Okay.
We start at 0.
Okay.
And from 0, whenever we get an A, we get to 1.
Okay.
And if we get a B, we are at 0.
Okay. So at 0, remember
At
that this
0
has to be a
as well.
function.
At 0
Remember
as
this
well.
is a function. If I get a B, then what happens?
If I get a B from 1, we get to 0, and from 0 as well, we get to 0 only.
So if I have a B, that remain in 0. Okay.
I remain in 0. From A, I get a B, I get to 0, and from A, 1, if I get an A, I get to 2.
Okay. If I get
And
a B?
At 2, I stay no matter what. If I'm at 2, I stay.
Whether I get A or B. And
A or
what
B.
is your final state?
Final state is 2.
Okay. Yeah. So okay, so can you?
This won't work, ma'am.
Why?
It can have 3 consecutive A's as well. So
That's fine. That does not say anything. How is that contradicting this set?
oh, means yes, 2 means at least 2. Okay, okay.
Ah, okay, yeah, sure. Contains at least 2. Yeah. Okay, so I also had a similar thing. Okay, so somebody said somebody misunderstood the question. What will you do in this case if I have contains equal to 2 consecutive A's?
Then from 2, if I get an A, I just get back to 0.
Yeah, but then you can just keep coming back, right? If you get an A, you get back to 0, let's say. But then you can have 1, 2, 3, 4, 5 A's consecutively. Right?
And maybe we can add another state 3 so that when we get a from 2, like we can't reach back from 3 to 2 anyhow. Like some.
Good. Okay. So you have to get used to it. Once you try these things, it will become easier for you. So you create a dummy state 3. If you get another A, you just stay here.
Yes, ma'am. So we can never reach 2 back from 3.
If you get a B, then you stay over here.
Ma'am, from 3,
Sorry?
if we get B, we shall go to 0.
Ah, sorry. From 3, if you get B, why will you go to 0? You can stay here, right?
So that
We can,
There can
Oh, no, no,
be
yeah,
two
correct.
consecutive A's later.
Correct.
like after the B, we can get another 2 consecutive
No,
A's.
this will not work. Because you can get,
No, I have a
Even
doubt.
then there is an issue. Like
yeah,
A
it's
B
fine.
A
This
will
is fine.
get
This
me
is
to
fine.
3.
This is fine.
Ma'am, A B A gets me to 3. Right.
A,
B A
B, A gets you to
3. But
correct.
that should happen.
Hmm. Okay, so try this out. So this is the question. You can try this out. We'll see. Maybe on Thursday we can see. So X contains exactly 2 so there is a substring where there are exactly 2 A's. So before that and after that you should have. So you should have this basically. So try this out on your own. We'll continue.
Ma'am?
Yeah.
3 A's, then 1 B, and then 2 A's. Is that a valid string?
For now, let's assume that is a valid string.
Oh.
There is one such thing. Let's say for now, one such thing has to be detected. So try this out.
Okay, ma'am.
I think now that I gave you this, you will be able to do it quickly. Anyway, try it out. Okay, so I don't have much time left. Let's try and finish this. So now we want one more useful property, that is delta hat q x y. So x and y are both substrings. Xy is the input string, and let's say I'm breaking it into 2 substrings x and y. Y need not be a single symbol. Then this should be equal to if the definition is fine, if the definition is according to our intuition, then this should be equal to delta hat of delta hat qx comma y. Intuitively this is what should happen, right? Because we are saying we are following a path labeled by xy. So following a path labeled by xy starting from s would mean after I follow this is need not be a simple path, I'm just drawing it diagrammatically. After I follow a path labeled by x, I reach p, and then I keep going, I keep reading y, and then I reach some q. So this is exactly what they are saying. Delta hat q xy if okay, I'll use some other name. R. So delta hat q xy, if it is R, I'll call this q as well. Then it should be same as delta hat qx, because these are functions. Because delta hat is a function, delta hat qx should then read as p, and then delta hat py should read as r. So intuitively this is what we expect, and the function also should behave in the same way. And what we need to show this, and one way of doing it is by inducting on the length of y. Okay, so I'll quickly go through the gist of the proof. So base case is if y is equal to epsilon, if y is the empty string, then you try and see that the LHS will be equal to the RHS. Okay, it's an easy exercise. Next is if LHS is equal to RHS for any x. This is important, that if y is an empty string, the LHS will be equal to RHS for any x. Similarly, another case is if y is a one length string, let's say A will be some, you can take any symbol from sigma. Then for any x, let's look at the left hand side. Left hand side will be delta hat q xa is equal to, by inductive definition, delta of delta hat qx comma a. A is some symbol, right? So we can use the inductive definition.
Yes, ma'am.
And now please mute yourself.
Are you married? Then I love you, ma'am.
Okay, so delta of delta hat qx a by inductive definition, and then since we proved that on length 1 strings delta hat and delta agree, notice that this is a length 1 string, so this can be rewritten as delta hat of delta hat qx comma a, which is exactly the right hand side of the expression when y is a singleton, y is a symbol from sigma. So now we for longer strings y, we are going to be using induction. The induction hypothesis will state that it is true for all x and all y dash that are strictly lesser in length than y. Now you consider the string xy, where y can be rewritten as y dash concatenated with a. So a is the last symbol of y. Then the left hand side is delta hat q x y dash a. This can be written in terms of the inductive definition as delta of delta hat q x y dash a. And again, since a is a length 1 string, this can be rewritten as delta hat of delta hat q x y dash a. Now you apply induction hypothesis over here. It can be applied on x y dash is strictly less than y. So this expression becomes delta hat of delta hat qx comma y dash. So we broke x y dash into the right hand side expression for delta hat q x y dash, and I kept a. Now you assume delta hat qx to be q dash. So you replace that expression, you simplify it to say that delta hat of delta hat q dash y dash comma a. And now again a is a length 1 string, so you can write this as delta hat of q dash y dash a. So it's a length 1 string, and we are using the base case 2, where we said no matter what your string x is, if the second half of the string is a singleton string, then right hand side is equal to left hand side. This will be the right hand side, this is the left hand side. Okay, so now you just replace q dash back, which gives you delta hat of delta hat qx comma y dash a, and y dash a now you write as y. So we started with the left hand side, ended with the right hand side. So we were able to show by induction that delta hat qxy is equal to delta hat of delta hat qx comma y, meaning that if I give you a string and I start from q, I break the string into two parts, x and y, then delta hat qxy will behave in the same way as if first delta hat was acting on q and x, and then whatever delta hat qx is, delta hat is now acting on that state and y, which intuitively is same as what should have happened in our transition diagram. Okay, so that's all for today. Any questions so far?
Ma'am, can you please explain the regular set concept?
Regular set is just so this the deterministic finite automata that we defined is an abstract mathematical model. Then we looked at a few examples where I specified what this tuple is going to be. I specified what the set Q is going to be, what delta is going to be, and so on. These are specific examples of deterministic finite automata. Each such example is accepting a set of strings, meaning it is, look at sigma star, a subset of sigma star is starting from the start state S is ending in a final state, and the sigma star minus that subset, all the strings that are not in that subset are ending in a non-final state. So each such specific example of a deterministic finite automaton accepts a set of strings. So any set of strings that has a corresponding deterministic finite automata automaton accepting it is called a regular set. Fine, or you still have doubts?
So string is accepted if and only if belongs to the regular set.
So consider a particular regular set. Consider why is it called a regular set? Because it is being accepted by a particular DFA. So a string in sigma star will belong to that DFA if and only if it is accepted by that particular DFA.
Okay.
So sorry, a string in sigma star will belong to that regular set if and only if it is accepted by that particular DFA.
Yes, ma'am.
But at the same time, it's not necessary that a particular regular set will have a unique DFA. There could be more than one DFAs accepting a particular regular set.
Yes, ma'am. That is possible.
That is possible. The other direction is not possible. If you have a particular DFA, it is accepting exactly one set of strings.
Okay.
The regular set contains every possible string that accepts that passes through the DFA, or if it has some strings, then it is fine.
Did not understand your question fully, but let me try and say it once more. So you have a set. This is a subset of sigma star. Okay. Now suppose there exists an M, a particular DFA M, meaning it has a transition function. It is some Q1, QM, sigma M, delta M, SM, and FM. So these are particular, you're defining it for this particular machine M. Now suppose it is true, so X belongs to, let me call this L, okay? X belongs to L if and only if delta hat SM X belongs to FM. Is it fine?
Yes, ma'am. I'm saying will the L contains every string X, or if L contains some strings of X, I mean some set of X that can pass through that.
So this is an if and only if condition. I'm telling you exactly which strings are in L. It's exactly those strings such that if you start from the start state of this machine M, you're going to end up in a final state.
Okay, it is set of every possible.
Correct.
I think, do you mean something like this? I think a language is called regular if you can design a DFA for it.
Yes. So A is a regular set.
Of course, we will see languages there for which you cannot design DFA. So these are not regular sets. Does that answer your question?
Oh, okay. Maybe that is the question. So, okay. So if your question was that whether any language has a DFA or not, that is not. That is not true. We are going to see examples where we see languages. Okay, we are going to see specific examples where we see languages that do not have DFAs accepting them. But as Professor Das has also showed you that there are uncountably infinite languages, and there are countably many finite definitions of finite representations of machines. Now, DFAs are specifically machines which have finite representations. So all languages we cannot expect all languages to be accepted by DFAs.
Okay.
Ma'am, for the exactly 2 consecutive ways, I did formulate something. I don't know if it is true or not. Can I say?
Okay, so do you have a class after this? Otherwise, I don't have a problem.
I have one. I'll just leave
You
after
have a
this.
class. Then why
Yes.
don't you? We have a Teams post, right? So why don't you post it there? You can share
Okay,
it
I'll
here.
post it there.
Yeah.
Okay.
or we can take it up on Thursday.
Okay, that will be better.
Ma'am, can a DFA have more than one final state?
Yes, a DFA. So in the definition of DFA, what did we say? A final states were a subset of the set Q or the entire set Q. It is possible that the entire set Q is the entire set Q is F.
Okay, ma'am.
So can you quickly tell me what will happen if all the states are final states?
All the strings will be accepted.
Correct. Yeah. And if let's say if S was not a final state, except for S, everything else was final state, then can you give me one string at least which will not be accepted?
Epsilon.
Correct. Okay. Okay, so we can continue on Thursday.
Ma'am, please repeat the previous question.
So suppose F was Q minus S. S is the start state. Then
okay.
Q is the entire set. So then at least one string that will not be accepted is the epsilon string.
Yes, okay. Got it.
Okay, so Thursday at 8 a.m. we'll have a tutorial on Thursday.